Good afternoon, y'all. Here we're going to go through the section 14, the review study guide for the Unit 3A chemical bonding test. So the first section has us sort statements into columns based on which are true, and they may fall into multiple columns. So I'm just going to highlight them here. Pink will represent ionic, yellow covalent, and green metallic. So first, those that conduct electricity as a solid are going to be metallic. Those that conduct electricity when dissolved in water are ionic. Shiny solids are metallics. Metals are lustrous. Metals and nonmetals form ionic solids. Crystal lattice could be describing both an ionic or a metallic structure. It's probably more likely to be talking about ionic, but could be both. Electrostatic attraction, meaning a positive and negative attracted to one another, is ionic. A sea of electrons describes metallic. The octet rule, both ionic and covalent substances follow the octet rule. Transfer of electrons is an ion. Delocalized electrons is going to be metallic. That's that sea of electrons. Nonmetal and nonmetal is going to be covalent. Malleable and ductile will be metallic. NaCl is an example of an ionic solid. Ionic solids are crystalline. Think of salt crystals. We do Lewis dot diagrams for both ionic and covalent substances. Covalent substances share electrons. Covalent substances are liquids or gases. Covalent substances make molecules. The crossover method is a way of determining the amount of ions in a substance. CCl4 is a covalent substance, and both ions and metals have high melting and boiling points. Covalent have low. So there's all our properties. Next, we'll get into a little bit about dot diagrams for a few ionizing atoms. So calcium, which has 2 valence electrons, in its normal state would look like this. And when it ionizes, it's going to lose those 2 electrons to form Ca2+. Sulfur has 6 valence electrons in its normal state. And when it ionizes, it's going to gain 2 more electrons to form S2-. Chlorine has 7 electrons in its base state, valence electrons. And when it ionizes, it is going to gain 1 more electron to form Cl1-. Lithium has 1 valence electron. When it ionizes, it will lose that to form Li1+. There's the first page. Next, we have the following intermolecular forces being ranked in terms of increasing strength. Well, the weakest are the ones that are present in everything, London dispersion forces, which are much weaker than dipole-dipole forces, which are much weaker than hydrogen bonds. Next, we're asked characteristics to help us determine. In London dispersion forces, all molecules contain London dispersion forces. Everything that's covalently bonded, everything that's a molecule has London dispersion forces. Dipole-dipole forces are experienced by all polar molecules. And hydrogen bonding occurs when H is directly bonded to nitrogen, oxygen, or fluorine within a polar molecule. So that is the most rare. Everything has this. Some things have both 1 and 2. And even fewer things have 1, 2, and 3. Next, we're asked about dissolving processes. Ionic solids like NaCl dissolve best in water. And then we have to remember for the covalent substances that like dissolves like. So something like a polar substance would dissolve in water, but a nonpolar substance is going to dissolve best in something like hexane, which is a nonpolar solvent. Now we get into the section where we're writing a little bit about each of the Lewis structures and answering some questions. So first, I'll go through and I'll identify that all 3 of these are covalent because they're all between nonmetals. My nitrogen, if I draw that, I have 10 valence electrons, and clearly, if I try to start sharing them evenly amongst that, I can't make everyone happy, so I have to start doing some double bonding. I'll erase one lone pair, turn it into a bonding pair. Everybody's still not happy, so I will erase another lone pair, turn it into another bonding pair. Now everyone is happy. This creates a linear molecule. This is a nonpolar molecule because it is symmetrical on both sides, and that means it has London dispersion forces. In CCl4, carbon tetrachloride, I'm going to connect everything. I should have, let's see, how many? I have 32 electrons to place. I've used 8, so I have 24 more to place, so I'll just put 6 on all 4 chlorines, and that should make everyone happy. This creates a tetrahedral molecule because I am 4 bonded atoms, 0 lone pairs. This is a nonpolar molecule because my central atom has no lone pairs and is bonded to 4 of the same atoms, meaning it only contains London dispersion forces. Next, I have H2O, which looks a bit like this. This is a bent molecule. It's bonded to 2 other atoms and has 2 lone pairs on it. It is a polar molecule because the central atom has lone pairs on it. For that reason, it has not only London dispersion forces, but also dipole-dipole forces. And this one happens to have hydrogen bonding because I see right here and right here that an oxygen is bonded to a hydrogen, which is one of our ones that we look out for. Next page, Al2O3 is going to be an ionic solid because Al is a metal and oxygen is a nonmetal. So here I'll draw my aluminum with its 3 valence electrons. I'll draw 2 of them because that subscript there refers to how many there are. I'll have 3 oxygens, each with 6 valence electrons. And I'm going to draw the transfer of those electrons there. It's going to get a little crowded here. For my final answer, I am going to just put it right here. I'll write that Al has a 3+ charge, and there's 2 of them. Oxygen has a 2- charge, and there's 3 of them. And I'll draw all 8 electrons that oxygen now has. I won't answer any of those questions because those only apply to covalent substances. Next, I have NF3. So I will connect all to my least electronegative element, the element in the center. And then I'll make the center guy happy before making all of the other guys happy with the remaining electrons I have. This is a trigonal pyramidal substance because it has 3 bonded electrons and 1 lone pair. It is polar because the central atom has a lone pair on it. And that means it has London dispersion forces, of course, dipole-dipole forces, and there's no hydrogen bonding here. In fact, I'm just going to go ahead and fill in London dispersion forces for all of my covalent intermolecular forces, because I know that all covalent, at the very least, have London dispersion forces. The reason I skipped these 2 is because they are both ionic substances. With CaCl2, I'll draw my 1 calcium, donating its 2 electrons to 2 chlorines. And I'll write my final answer, which is Ca2+ and Cl with its electron. It's just 1- because each chlorine only gained 1 electron, but there are 2 of them. And again, we don't have to answer those questions because this is an ionic substance. For Na, we have, or Na2S, we have a little bit of the opposite, where we have an anion that wants 2 electrons, so 2 sodiums are going to have to donate those. So for my final answer, we'll write Na, 1 plus with a 2 there. We'll draw S with all of its valence electrons there with a 2 minus charge. For CS2, when we connect these, we get that they need to double bond, and that's because there's a limited amount of electrons. This is a covalent substance, of course. I might as well work through that one in case y'all are still struggling with double bonds. So CS2, we have 16 total electrons to work with. So if I single bond everyone, I have now used 4, so I have 12 left to place as electrons. I'll do 2, 4 on the middle guy, then 6, 8, 10, 12. Now I'm out of electrons, but the sulfurs are not happy, so I'll turn a lone pair into a bonding pair there. The sulfur on the right is still not happy, so I'll take another lone pair, turn it into a bonding pair. And that's why we double bond. Now, this CS2 is a linear substance because it's bonded to 2 atoms and has no lone pairs. It is going to be nonpolar because the central atom has no lone pairs and is bonded to only the center, the same type of atom. So that means it only has London dispersion forces. And we're good there. PCl5 is a bit of a big one. We have phosphorus connected to 5 chlorines. It has an expanded octet, but each one of those chlorines is going to be full because we have 40 total valence electrons to work with. So we have 30 that we can place in lone pairs after subtracting the 5 bonding pair. We won't worry about the shape here. This is a non-polar substance because the central atom is connected to all the same types of atoms and has no lone pairs, meaning it only has London dispersion forces. Next, we have PH3, another covalent substance, which if we draw it out, should look like this. This is a trigonal pyramidal substance because we have 3 bonded atoms with 1 lone pair. It is a polar substance because the central atom has a lone pair on it. Therefore, not only do we have London dispersion forces, we also have dipole-dipole forces, and there is no hydrogen bonding here because those hydrogens are not connected to an N, O, or an F. Lastly, we have selenium dichloride, where we'll draw our selenium connected to our chlorine. We'll make our selenium happy. We'll try to make our chlorines happy, which we are able to do without running out of electrons. This is a bent molecule where you have 2 bonded atoms, 2 lone pairs. It is polar because the central atom has lone pairs on it. Therefore, it also experiences dipole-dipole forces, but it does not experience hydrogen bonding. So watching through this, hopefully, best summarizes all the remaining work we have between Lewis structures, identifying intermolecular forces and dissolving, and going through some of the different properties of each of the metal types. Hope you enjoy, and good luck studying. Thanks.